Hello, everyone. Let's start this lecture. Before starting this lecture, let's quickly see what happened in the previous lecture. So in the previous lecture, we talked about an infinitesimal dipole antenna. So I'm just going to write it here, infinitesimal dipole antenna. So the assumption with this antenna was that this is extremely tiny. So for example, less than lambda by 50 or equal. And also we assume that the current on the dipole, so if this is, let's say, Z axis, if this is the current axis, so we assume current is uniform. So I naught. Again, this is a uniform phasor, so it's still time varying. So, and then we mentioned that if you want to have uniform current, you of course need to have top loading. Otherwise, the current has to go to zero at the end. So this, and then with that, we got this equation for radiation resistance, AT pi 2 L lambda square. And this was our equation. And just one thing about this equation, if you remember E and H in the far field for this antenna, you realize that A was proportional to L, E therefore was proportional to L, H was also proportional to L. But remember, this radiation resistance is essentially related to power. So we have radiated power is equal half RR I naught squared. So you could somehow guess that because power has to do with E cross H or E times H complex conjugate, then you essentially have a multiplication of these two. So this becomes L squared. And because in antenna, everything is with respect to wavelengths, you get this L divided by lambda square here. Now, let's see what sort of radiation resistance we might have. So let's plug L equal lambda by 50, which based on our definition is the maximum case based on which we define infinitesimal dipole. If we plug that here, of course, lambda will cancel and you get AT pi square 1 divided by 50 square, and that should be around 0.3 ohm, if I'm not mistaken. Let me double check that. Yes, that's about 0.3 ohm. And as you see, this 0.3 ohm is so small. That's why it's not a good antenna. So remember that the transmission line that brings the power to the antenna is often a 50 ohm characteristic impedance. So you could easily imagine that with this antenna, you're going to have problem in terms of impedance mismatch and so on when you go from 50 to 0.3. But remember, you're not going to 0.3 by itself, because we haven't really discussed the storage of energy around this antenna. If you go back and look at the power density, you realize that this antenna in fact stores energy, and the storage of energy is in the nature of capacitance, and you can somehow guess that it's capacitance. So you essentially have also a capacitor as part of the antenna. And the way to realize that, remember, this a small dipole antenna is in fact was an open circuit transmission line. So this was open circuit, and then we started bending these arms upward and downward and made it an antenna. But if this is tiny, the Z in of transmission line, you can calculate that, and this becomes in fact capacitance. So if I want to do that, let me do it quickly. So Z in of a transmission line is Z naught plus J ZL tangent beta L, ZL plus J Z naught tangent beta L. Now, what is our ZL? Z of load is infinity. So this is very large. This is very large. So essentially, I can ignore these two. So it's going to become Z naught, ZL, JZL, tangent beta L, because ZL is infinity, open circuit. So ZL cancel. So I get this. You remember 1 divided by J is negative J. So it becomes negative J Z naught tangent beta L. Now, if L is tiny, remember beta is 2 pi divided by lambda, L is length. Just a side note here is that I called the whole thing L. So if I call the whole thing L, this is in fact L divided by 2. So L divided by 2, L divided by 2, this becomes L. So if I want to be accurate, I need to have L divided by 2 here. So, but in any case, remember that if L is a small compared to wavelengths, tangent is positive. So this is positive, but then you have a negative sign, so your Z in becomes negative. So Z in becomes J times a negative number, which is a capacitor. So essentially this, but from the very beginning was a capacitor. So when you make it a dipole, it is still a capacitor, but then because this dipole antenna radiates, you're going to have a radiation resistance. This one didn't have a radiation resistance. And this method that I use for Z in is an approximate method. So you shouldn't always apply it, but it gives you some good intuition. Sometimes it's not precise, and we'll probably going to see one case that is not precise, but it still gives you good intuition. Now I wanna start my next step, and in the next step, what I like to do, I'd like to actually consider dipole antenna, but this time I want to go to the category of a small dipole antenna. And a small dipole antenna, the thing that happens is that I'm going to increase this L. So this time, for example, my L is greater than lambda by 50. Before was a smaller, and between lambda by 50 to lambda by 10. Now, I call this a small dipole. So essentially what's happening is that, for example, look at this dipole that I have. So this is a dipole, and you can always change the length. So for example, in this case, this is the dipole from the lab volt system. I can have a longer wire, and now this become a new dipole. So essentially, I'm changing the length of the wire in these cases. So this one that I just showed you wasn't a small dipole antenna. I just wanted to show you that this topic that we are discussing, we're changing the lengths. So I want to know what's going to happen with this small dipole antenna when I change the lengths. So let's check that. So keep this in mind. I'm going to come back to that, and then let's focus on this. Now, if I want to start this, you could say, okay, what kind of current distribution you're assuming on this a small dipole antenna? Are you going to assume a uniform current, the same thing that we had? This was Z. If this is the axis of current, this is the uniform current. I'm not going to assume uniform current for this one, because this one, you need to do some extra step to make it uniform current. I want to be more practical with this one. And practicality means the current needs to go to 0 at the end. So I'm not going to assume uniform. So this assumption of uniform current that we had in the previous step is gone. I'm going to assume that the current, in fact, goes to 0. So let's see what would be the current then. So remember, dipole antenna comes from an open-ended transmission line. So this is the current on the transmission line. Now, if I choose a small piece of this transmission line, so if this is the current on the top wire, on the bottom wire, I exactly have the opposite one. So this would be one piece of current here, this would be another piece of current here. So if I start bending from this point upward here and downward here, so what I'm going to have would be one small curve here and another small curve here, something like that. So this would be my current. And again, as you notice here, the current at the end, so this is point A, point B, this is point A, point B. This needs to be 0 because this is an open circuit here. So, and this is open circuit. But there is one simplification here, which is very useful for us. And let me go to that simplification. So before going for that, I'm going to plot you a sinus wave. So this is my sinus wave. Now look at sinus. Sinus, of course, has some curvature. And this is, if you remember, this is lambda by 2. This is lambda by 4. And remember, what was the size of a small dipole? Lambda by 10 and lambda by 50. And if the total length is lambda by 10, one arm maximum would be lambda by 20. So let's assume this is lambda by 20. So if this is lambda by 20, I only need this a small portion. And if you look at this a small portion over here, you see that if the sign is in the beginning, it is almost like a straight line. And you know that from mathematics, remember sine of x when x goes to 0 is the same as x. That essentially means if you plot y equal x and also sine of x, these two in the beginning would be very similar. So that's the idea here. So if I assume that this is a straight line, instead of assuming some curvature here that's going to make my mathematics more complicated, I can assume that this is a straight line. And if that becomes a straight line, then this becomes my current distribution. So this is, if this is the current axis, you can plot it like that. So this is your I naught. So you see here, this is essentially becomes the current distribution of a small dipole antenna. We call it triangular current distribution. And that's the justification for triangular current distribution. Therefore, if I want to write the current distribution for this small dipole antenna, this would be my current distribution. IZ would be equal to, so I can say, for example, top arm where Z is from 0 to L divided by 2. That's going to be I naught 1 minus 2L Z. I mean, this can be proved, and you can look at my notes to understand it, but I'm going to discuss it shortly. But it can be proved based on sinusoidal current, so you can get to this. And the other one becomes I naught 1 plus 2L Z for Z greater than minus L divided by 2 to 0. So this is Z equal minus L divided by 2. This is Z equal L divided by 2. This is the bottom arm. Now, and both of them are in the Z hat direction, of course. So if I make it a current here, so this is Z hat, this is Z hat. Remember, when you make the dipole antenna, these two currents become in phase, essentially, and that's why it radiates for you. So now, if you consider this one, let's check a couple of things. What's going to happen when Z is equal 0? When Z equals 0, you can either substitute here or here. If you substitute Z equals 0, you get I naught. Correct. Now, what's going to happen if Z is equal L divided by 2? That means you're here. If you substitute Z L divided by 2, you get 1 minus 1, 0. So you get 0 current, which should be 0 current. When Z is a minus L divided by 2, you again get 0, which is what we want in this case too. So that's essentially what we have in this case. So as you see, everything matches perfectly. So this is my current distribution. Now that I have my current distribution, I can, in fact, start finding magnetic vector potential to get to the far field of this antenna. So I essentially need to integrate these two currents. So let's start our integration and see what we're going to get. Okay, so let's plot the antenna in the coordinate again. So if this is my Z, if this is my X, if this is my Y, I assume this is my antenna, and this is my observation point R, and R prime, remember, R prime is the vector that connects from origin to different points on the antenna. Why I'm saying different points? Because you integrate over R prime. So essentially you get different points. And remember, this antenna is on the Z axis. So I made it a little bit shiftier. Maybe I should fix that so there would be no confusion. So the antenna is right on the Z axis like this. So this is my antenna, and remember the current distribution is triangular. This is a small dipole. Okay, so now what is our first step? Finding the magnetic vector potential. So let's find it. A R, so that means magnetic vector potential at observation point R is equal to mu naught 4 pi j r prime e to the power of minus jk r minus r prime divided by r minus r prime dv prime. Now, similar to before, this antenna is so tiny. So remember, the length of the antenna is smaller than lambda by 10. So that means this R prime that you have here, each arm maximum is lambda by 20, is lambda by 20. So even if you are a few wavelengths away from the antenna, it's still R minus R prime in both the phase term, J something is the phase term, and the amplitude term in the denominator. You can approximate it by just R because R prime is so tiny. So that's what I'm going to do. Therefore, I'm going to simplify that to AR mu naught 4 pi JR prime e to the power of minus JKR R dV prime. So now I don't have my R prime here, so I can simply take it out of integration. So I can easily do that. This can come out of the integration, and that becomes mu naught 4 pi. So I was supposed to take this out like this, and then I'm going to have this. Now, remember, this is the current in general, but the current that I have is essentially current on a line. So I can just write it specifically for my case. So this element of integration would be element of length because the current is on a line, and the element of length is dz. So it's going to be dz. So I'm going to have mu naught 4 pi e to the power of minus jkr r. And the current is in the z direction. So I'm gonna have z hat, and this becomes I z prime dz prime. So this becomes my integration. But remember, I have two arms, and I had two equations for the two arms. So I can potentially do this. I could say mu naught 4 pi e to the power of minus jkr r z hat. And now I'm going to have two integrals. One of them is going to go from minus L divided by 2 to 0, which is the bottom arm. And I'm going to have I naught 1 plus 2L z prime dz prime. The other one would be for the top arm. So I had two expressions for current, top arm, bottom arm, and I can calculate it and I can find it. But do that for yourself, but then you could also notice something, that what is the meaning of this integral here? The meaning of this integral is the area under this curve. So, you don't really need to calculate that. You can just have it because that's a triangle, and the height of the triangle is I naught, and this length is L. So the result of this integration, if you do it, should be the area of the triangle, which is I naught L divided by 2. Height times this side divided by 2, and that would be the result of that. And I can just write it as it is. So it's going to become Z hat. I have a half. then mu naught 4 pi I naught L e to the power of minus jkr r z hat. This is what I'm going to have for my A at the observation point R. So my A is Z hat, and this is the expression for that. Now, based on this expression, what's the next step? You convert Cartesian coordinate to a spherical coordinate to get your A R, A theta, A phi. You essentially don't need AR because I'm not going to consider near field. So you can just ignore it. I don't really need that. So then the next step, you get your E in the far field and phi in the far field. And you know that in the far field, ER is 0. After that, you get your H by plane wave equation. So now this is the whole procedure. Now, why didn't I go through this? I'm going to tell you why in a second. But this is essentially the procedure that you can follow. Now, why I didn't go through with this? Because I did it one time already for infinitesimal dipole antenna. Now, you might say it could be different, but I tell you why it's not different. Check your notes or check my video for infinitesimal dipole antenna. You see that this was my A for infinitesimal dipole antenna. So let me write it for you. AR was Z hat mu naught 4 pi I naught L e to the power of minus jkr r Z hat. This was for infinitesimal. This new one is for a small dipole. So you see that they're pretty much identical. There is only one difference. This one has half, this one doesn't have half. So this is the only difference. And you expect this difference, right? Because remember, in infinitesimal, we assume the current was uniform. So if this is the current axis, if this is the Z axis, this was I naught. So the area under the curve became I naught L. So you had an I naught L. But now with this new antenna, we had this. And if this is I naught again, this is L, the same as this L, then the area under the curve is I naught L divided by 2. That's why you get a 2 in the denominator here. Something that sometimes people make mistake when they're connecting these things. So you see the mathematical expression here is pretty much identical. But remember, L for infinitesimal is less than lambda by 50 or equal lambda by 50. This L is larger. So don't think that this is exactly half of that when you plug numbers here. It's not going to be, because you're going to plug a different L for both cases. But in terms of mathematical expression, this is just an extra half here. So that's for a small dipole. Now, based on that, I can actually use what I derived for infinitesimal dipole antenna and do the same thing for a small dipole antenna without going to the same math. So let me see if I have the expression here. So the expression that I had for infinitesimal dipole antenna is this. So this one resulted in E theta, which was theta hat J eta K I naught L sine theta 4 pi e to the power of minus jkr r. So this is what I had, and then of course I'm gonna have an h phi, which h phi would be e theta divided by eta. So eta times a smaller, and this is gonna be h phi. So this was for infinitesimal. As you know, I prefer to keep usually e to the power of minus jkr and r together to show that this is like a spherical wave that going out, but instead of spreading the power equally on this spherical area, I am tailoring it with angular distribution of sine theta. So this is what I try to show when I put that aside. So it's like if this is the case, this is like an isotropic case. So it's everything is equal on the surface, but then you favor some angles over the other angles. So that's the sine theta over there. Now, this is my E and H for the infinitesimal dipole antenna. And remember, this E is directly related to A because E, remember, E theta was minus j omega A theta. So if you double A theta, E becomes double. If you make it half, E becomes half. Now look at the mathematical expression. The A of the small dipole antenna is half of A of infinitesimal. So if I write the E for this one, E of this one would be half of the E of the infinitesimal dipole antenna. So I can just write that. So let me write it down. So E theta of a small dipole antenna would be this, but divided by 2 because its A is half of this. So that's going to become theta hat j eta k I naught L sine theta. Now instead of 4 pi, I'm going to get 8 pi. E to the power of minus j k r r. So this is going to be the case for a small dipole antenna, and of course h phi in the far field is eta times smaller than E theta. That's the far field zone, of course, so I can emphasize it here too. So that's the situation that I had. Now let's also consider another thing that we had for infinitesimal dipole antenna. What was that thing? That thing that which is important, because with E and H, it's really difficult to understand in terms of quantitative value, how does this antenna do compared to a standard antenna. So if you write the directivity for this, directivity, which is a function of theta and phi in general, becomes 1.5 sine 2 theta. That's what we had for the infinitesimal dipole antenna. So the directivity of infinitesimal dipole antenna was this. So what's the meaning of that? First of all, it means that the maximum directivity is 1.5. Where does it happen? In theta equal 90. And it also says that the directivity doesn't depend on phi, because if you go around the antenna, you see the same thing. But the maximum is at theta equal 90. So theta equal 90 is here. So if you give some power to this antenna, this radiates 1.5 times better in theta equal 90 compared to isotropic antenna. But on the other hand, at theta equals 0, it doesn't radiate. So now my question for you is that if this is E theta D of infinitesimal antenna, what would be the D of the small dipole antenna? So let me write that with red color so that things related to infinitesimal, we have it in red. So this is for infinitesimal. Now, this is my question. What would be d theta and phi of a small dipole antenna? If you know this is for infinitesimal dipole antenna. Now, let's see what we're gonna have. So what is the definition of directivity? Definition of directivity tells us that this is u theta and phi in the numerator divided by u theta and phi of an isotropic source, which is p radiated divided by 4 pi. So you can write it as 4 pi u theta and phi p radiated. Now, what is, if, for example, isotropic antenna, if, for example, infinitesimal dipole antenna has a U And in fact, we derived the U for infinitesimal dipole antenna. What would be the U of a small dipole antenna? Because this is the U of a small dipole antenna. What would be the relation between U of a small dipole antenna and U of infinitesimal dipole antenna? So you would say, okay, what is U? U has to do with E and H. Okay, U comes from power density. So you need to multiply E and H. Now, you know that E of a small and H of a small is half of E of and H of infinitesimal. So if I multiply them, half and half would be 1 divided by 4. So here I can just say 4 pi, and then I'm going to have U theta and phi of infinitesimal divided by 4, because U is essentially E and H are both in U, so each of them is half. The whole thing would be divided by 4. And the same thing for power. So the power radiated by this antenna, and this antenna, in terms of mathematical expression, would be, for this a small dipole antenna, would be infinitesimal divided by 4, because power is also related to E times H. So I could write here P rad of infinitesimal divided by 4. So if I have that, these cancel, and now I have just infinitesimal, therefore I'm going to get exactly the same directivity. So if this is the directivity of infinitesimal, if you calculate the directivity of a small dipole, you could do that without going through this similarity. But I thought I'll do it this way for you, and then you can calculate it for yourself and confirm this result. This is going to also be 1.5 sine 2 theta. This is going to be the same thing. So I have the same directivity as well. So that's another thing to keep in mind for this antenna as well. And if you remember the half, we also derive half power beamwidths of this antenna. We need to make equate directivity half of its maximum, and we equate directivity to half of its maximum, which is half of 1.5, and it became 90 degrees. Because this is the same directivity distribution, therefore half power beamwidth of a small dipole antenna is also 90 degrees. So that's another thing that we have for this in a small dipole antenna. Now let's move on with one more thing. And the thing that I like to mention was the radiation resistance of infinitesimal dipole antenna. We got 80 pi 2 L lambda to the power of 2, which we studied in the beginning of this lecture. Now, what would be the radiation resistance of this small dipole antenna? So what would be the radiation resistance of this small dipole antenna? Now, if we want to figure out radiation resistance, let's start with the equation that we are deriving that. So we say P rad is equal half RR I naught squared. Now, imagine here P rad should be P rad of a small dipole antenna. But what is the relation between P rad of a small dipole antenna and P rad of infinitesimal dipole antenna? So P rad has to do with E times H. So to be precise, E cross H complex conjugate. So you need to multiply these two. But remember, for a small dipole antenna, E and H are half of E and H of infinitesimal. Again, look at 8 pi versus 4 pi here. So if E is half of this, H is also half of this. So when you multiply that, this becomes essentially 1 divided by 4 of P rad infinitesimal. So this is the situation that we're gonna have, and so you need to keep this in mind. And if this becomes 1 divided by 4, then what's gonna happen to RR in this case? So this is something that we want to see in this case. So let's look at RR, and the RR that you're going to have would be 1 divided by 4 P rad of infinitesimal. So this is what we have here, divided by half I naught square. So this is what we have. And if we go by that, then what we're gonna see would be RR essentially becomes 1 divided by 4 of this one. And this one is already the radiation resistance of infinitesimal dipole antenna, because we have the power of infinitesimal dipole antenna here. So we could argue that radiation resistance of a small dipole antenna would be 1 divided by 4 of the radiation resistance of infinitesimal dipole antenna. So if I go by this logic, I could write that without deriving it. Of course, you can derive this, and I'd like to ask you to derive this for yourself, but then I want to do it this way so that you can get better intuitive understanding of what's going on. So this becomes 1 divided by 4 of this, and that becomes 20 pi square L lambda square, 1 divided by 4 of this. So this is the radiation resistance that you're going to get. Now, at this point, always we have some confusion. So when you look at that, you might say something which is, you might see something which is counterintuitive to you. And the thing that's counterintuitive here is that this was, if this is, for example, the size of this antenna, and then a small dipole antenna is of larger size, and you see that the radiation resistance is in fact smaller than this. And you might say, okay, I know that if I increase the size of the antenna should be a better antenna. It should radiate more. So I'm expecting more radiation resistance on this side. Why this is a smaller? In fact, this is not a smaller. This is the same mistake that I mentioned you might make in the beginning of this lecture. You see, in terms of mathematical expression, this is 1 divided by 4 of this. But in terms of the actual value, that's not the case. Because in this one, for infinitesimal dipole antenna, you need to substitute L equal lambda by 50, and you get about, in this case, 0.3 ohm. So this is L equal lambda by 50. But with the small dipole antenna, L could be lambda by 10. So you substitute lambda by 10, and you're going to get RR, which is around 2 ohm. So you see, from 0.3 ohm, we arrived at 2 ohm. So that's the increase in radiation resistance, and it tells you that you have more radiation in this case. So a small dipole antenna is a better antenna if you compare these radiation resistance. The reason that in mathematical expression this does not show is that we helped infinitesimal dipole antenna with top loading. So if you look at the current here, this was uniform, this was triangular. So we weren't comparing two same thing. This current distribution and this current distribution was different. So we were helping this one without helping this one. That's why mathematical expression shows this fact. But even with that, when you substitute for the actual lengths, you're going to see that this antenna can in fact outperform the other antenna. So this is what we have right now in terms of a small dipole antenna. Now, the natural next step is to increase the lengths even more, because even with 2 ohm, you see it's not a very good radiation resistance. So as you see, when we go to a longer antenna, like for example, half a wavelength dipole antenna, this value gets closer to 70 something, which is much better when you compare it to 50 ohm characteristic impedance of the transmission line. So the next step would be to see what's going to happen if my current distribution is sinusoidal, because if it's not too small, I cannot make this triangular distribution assumption. Okay, so we just saw that if the length of our dipole antenna is so tiny, the radiation resistance won't be good. So in terms of impedance match, we have problem. So we then said we want to increase the length of dipole antenna. So if I increase it, then I cannot use this triangular distribution anymore. And I need to assume that the current distribution on the dipole is sinusoid. So let's start with that. So the reason we are assuming that it's sinusoid is essentially is because we are starting from our open-ended transmission line. So remember, we have this open-ended transmission line, and this is an open circuit, of course. So when the wave, a voltage wave travels here, when it hits the open circuit, it reflects back. So when it reflects back, you're gonna have a standing wave. So remember, the wave that going this way is e to the power of minus jk. Let's call this, for example, x, for example, e minus jkx. The wave that reflect backs is e to the power of plus jkx. So you get both of them. And if you remember, sine of an angle is e to the power of j theta minus e minus j theta divided by 2j. So when you have these two exponential like that, you essentially get this sinusoidal current distribution, which is the indication of, in this case, our standing wave. Now, if you start turning this at arbitrary lengths, let's say at this length, then what you're going to have essentially this sinusoidal current distribution at the dipole antenna. For example, let's make an example. For example, let's assume I have this open-ended transmission line, and this is my current distribution, and of course this is half a wavelength. So, and this is like that. Now, this would be the other current that I have. And if I start bending from this point, if this is my A point, B point, let's call this A prime, B prime. If you start bending this way, bending this way, then what you're going to get would be these two sets of currents, which are now have the same direction. And the current distribution, if I assume that the current distribution stays the same as the transmission line, which is a reasonable approximation, so you have a half sinusoid here, so you get this, and then you get this as well. So this becomes the current distribution on the dipole antenna. You could do a different case, for example, and this time, and remember, this was half a wavelength, so in this case, this is one full wavelength dipole antenna. Now, if you consider another one, which is the famous dipole antenna, now this time you get lambda by 4. So if you get lambda by 4, and this is also lambda by 4, so what's going to happen is that you're going to get this, which goes to the maximum, and then again this, which again arrives from here. So you get essentially half of sine if you go from here to here. So let me be clear, A prime, B prime, and this is the same thing, A prime, B prime. And this is my A prime, this is my B prime. So you get this now with upward currents in this case. But remember, these currents, they follow each other in the terms of direction. So if they're going both upward and at a different time, both downward. So this is going to be the current distribution that I have. And as you see, it's essentially in the form of sinusoidal. So now, what I need to do is now to have an expression for currents on these two arms of the dipole antenna. And the expression is, of course, sinusoidal. So I can say IZ, assuming that the dipole is along the Z axis. It's going to be I naught sine k wave number L2 minus Z I naught sine k L2 plus Z, and this is for the top arm from 0 to L divided by 2. Sorry, this is Z, so the Z is from 0 to L divided by 2. In this case, 0 is from Z is 0 to minus L divided by 2. Now, if you, for example, substitute L divided by 2 in here, so that would be this point, L divided by 2, Z equal L divided by 2. You see that it's sine of 0, so the current vanishes. If you substitute Z minus L2, which in this case you are here, that's Z minus L2, then you see the again current goes to 0. And if you are at the center and substitute Z equal 0, then you get a different expression, and for both of them would be the same, because at Z equals 0, we arriving at the excitation port. So that's the current that we have, and now I need to go and find magnetic vector potential for the general case. That would be my general current distribution. And by the way, you can turn that into triangular current distribution by assuming that L is very small compared to wavelengths. Remember, K is 2 pi lambda. So here you have an L that's going to be multiplied by that. So if you look at L divided by lambda here, if that's small, you can approximate sine of x by x, and you can carry on, and you get to your triangular current distribution. So now I need to start performing my integration. So for the magnetic vector potential. So if I want to calculate that, I'm going to have AR. So let me perhaps remove everything and start from here. AR is mu naught 4 pi J R prime e to the power of minus jk r minus r prime dv prime. Now, so what we have here is this integral, and we know that our current, similar to the previous cases, is on a dipole antenna, so it's on a line. So we can change that into mu naught 4 pi, and I'm going to go with the top arm first, so 0 to L divided by 2 sine of k L2 minus Z e to the power of minus, I can put it Z prime to say this is the source. Anything source would be prime based on our standard. And then D becomes D along the dipole antenna. And then I'm going to go now to the bottom arm from minus L divided by 2 to 0 sine k L2 plus Z e to the power of minus jk r minus r prime dz prime. So this is essentially what we have. So this is the sign that we have here, and this is our expression. Now, one thing that's now deviates from our previous discussion is this term here. So let's go back to it. So this is now our dipole. I'm gonna plot it a little bit longer because I'm not limiting myself to very small lengths. So, and this is your observation point R. And now imagine, for example, if the length of the dipole is 1 lambda, then this vector, which connects me to the tip of the dipole, is R prime, which is equal to lambda by 2 Z hat. So this is now 1 R prime. For example, it starts from the origin and it connects you to the top of the dipole antenna. So it is lambda by 2 Z prime, assuming that the total length of dipole is 1 lambda. So as you see in this case, maybe having r minus r prime equal to r is not the best approximation. So in this case, we need to come up with better approximation. So, and the better approximation, you're going to see that we're going to use the same approximation for the amplitude term, but for the phase term, we're going to enhance it. And that would be the beginning of my discussion in the next class. Thank you very much.